Our next speaker is Zhihui Wang.
So my name is Zhihui Wang. I'm from the Quantum AI Lab at NASA. So I'm going to talk about the phase transition in single machine scheduling problems. This work was done in collaboration with our colleagues in the Planning and Scheduling Group at NASA and University of Toronto. So an outline. I'm going to show you the solvable, unsolvable transition in single machine scheduling problems. And we identify such phase transition in both tractable and intractable problem families. And I'll talk about how the transition correlates with the problem hardness. So a little background. Back in early 1990s, Cheeseman, Konevsky, and Tyler, also at NASA, asked a very important question. Where are the really hard problems? So I'll take their original graph here and highlight the 3 set. So take 3 set as an example. They conjectured that when you can identify a solvable to unsolvable transition, then the hard problems lie at the transition. So for example, 3 set. There are 2 parameters. One is the number of clauses, the other one is the number of variables. And if you take the ratio of these 2 as the control parameter, as the ratio goes from 0 to infinity, the problem goes from under constraint, because each clause is a constraint. When it's under constraint, there are lots of solutions, and it's easy to find one. When it's over constrained, most likely there will be conflicts. So it's easy to show that no solution exists. While when it's critically constrained, that's where you can't easily find a solution, can easily show there's no solution, so the problem is hard. So we studied the phase transition in single machine scheduling problem. This is a problem that's of great interest at NASA. For example, I show a few pictures here about telescope, spacecraft, and Mars lander activity. They all concern single machine scheduling. So what is a single machine scheduling problem? We call it SMS. So we're given a set of jobs to schedule on a single machine over time. So each job, this is the time axis, each job has a fixed constant release date, which is the earliest time that you're allowed to schedule the job, and a fixed deadline, and a fixed processing time. So there are lots of jobs. Here I show a valid schedule. So the goal is to schedule each job within its time window and no jobs overlap. So a decision version of this problem is to ask whether such a valid schedule exists. We call it the solution. And this problem is NP complete. So why we study, there are lots of scheduling problems. Why single machine scheduling problems? We say that, as we saw in SAT, typically for the problems typically studied for phase transition, there are very few parameters, typically just 2. While for realistic scheduling problems, there are too many parameters. It's hard to identify a phase transition. So SMS is a simple scheduling problem. We see there are relatively few parameters: a release date, a deadline, a processing time, and a horizon. Yet we'll show that it's simple. It'll still show interesting phase transition behavior. So ideally, there are 4 parameters. We can identify the phase transition in this 40 parameter space. But of course, that's challenging. So a natural start is to fix some parameters and to reduce the dimension. So what to fix and how to fix? One way is consider identical processing times for all jobs. But that problem family turns out to be tractable. Another one is consider 2 processing times. One is 1, the other is a constant. That's also tractable family. And we can also consider fix the window size to be constant, which is the deadline minus start date, the release time, sorry. This is also tractable family. And now we consider 2 processing times. We show that if is different by 1, that's also a tractable family. So we actually found phase transition in all these tractable families. So this phenomenon is similar as the case of 2-set, where there are relatively hard instances around the phase transition, but the whole problem family is tractable. So now, we still consider 2 processing times, non-unit, non-different. So it has been shown that in this case, the problem family is NP-complete. So we're going to focus on this problem family. So what we're going to do is we fix the two distinct processing times to be constant and consider two control parameters. One is horizon. The other one is we allow all jobs to have a maximum window size. So each job, the window is randomly, uniformly drawn from its processing time to the maximum window size, Wmax. So what we expect to see is, if you color the probability of solvability, green for unsolvable, yellow for solvable, and highlight the transition in blue. So we normalize the horizon by n is number of jobs, p is the average processing time. So this is the minimum horizon that can fit all jobs. So apparently when this value is 1, the problems tend to be unsolvable. While when the horizon goes to infinity, it's under constraint, solvable. And similar here, when Wmax is comparable to the horizon over here, jobs can almost freely move around the horizon. It's solvable. While when Wmax is very small, jobs have no room to wiggle. It's unsolvable. So this is basically what we expect to see. So where would the blue band be? Somewhere around here. So now the numerical results. We see the blue band as we expected. Unsolvable, solvable, the transition frontier. Good. Now, to call it a phase transition, we need another, satisfy another condition, which is, so this is for 40 jobs. As we increase the job size, say here, to 200, we see that the transition band gets sharper. So that's a key feature of the phase transition. So now we've identified the phase transition. It's a 2D phase transition in this NP-complete problem family. How about the hardness? So on this 2D map, at each data point, we draw 1,000 instances. And for each instance, we solve it by we use the CP optimizer and record the number of nodes explored in the search, as we typically do in computer science. We use this as a measure of the empirical hardness. And the color shows the logarithm of that number. So the first observation in hardness is that there are very rare relatively hard instances. Typically we check the median, but for median we didn't see anything. So we go for higher percentile. So this one shows for 99.5 percentile, we see some hard instances. When we go for 99.2, we see a few more. So the same thing happens for 200 jobs. At 95, not much. At 99, we see some. So very rare, relatively hard instances. And now, if we compare the location of the hard instances, which are these warm spots, with the location of the phase transition, see, they're around there, but kind of scattered. So we claim there's loose correlation between the phase transition and the hardness of the problem instances. So this is basically what we have. As a summary, So we empirically identified solvable, unsolvable phase transition in both tractable and intractable problem families of single machine scheduling problems. And for the intractable family, we know it's intractable. Surely there are hard instances, but typical instances are easy. And that the hard instances, which are very rare, correlates loosely with the phase transition region. So I'm gonna end with the open questions. So for SMS, we still don't know what are effective ways of locating or generating hard instances. I'd like to make a note about our results is that we couldn't test whether the empirical hardness increases exponentially with the problem size because they're so rare, so we can't rely on the statistics. So if we find such hard problems, then the next step would be use them to benchmark solvers, including novel methods like what our group is for, quantum computing. And moreover, this is the original question posed in 1991. I would say, in some sense, it is still an open question. So we still would like to ask under what circumstances there's a close relation between phase transition and hard problem instances. And welcome to the poster session for more details, and if you're interested in quantum computing and planning and scheduling. Thanks.